When applying the fundamental operations of adding, subtracting, multiplying, and dividing to functions, the situation is handled in exactly the same way we would expect. For example, if we have these two functions and we want to add them, we would describe the addition as f of x plus g of x. Well, just replace f of x with the expression, g of x with its expression, and then add the two expressions. Here we're dropping parentheses and collecting like terms. A notation that's used to describe the addition of functions is this. It's f plus g of x. It's the addition of the two functions, and x is the variable involved. So f plus g of x would be the 5x plus 4 that we found here. Now we can use this kind of notation to indicate subtraction like this. So this means the difference of the two functions, but I suggest that we write this the way we would understand it. This is f of x minus g of x, you see. And now the substitution is particularly easy. The f of x function, the g of x function, the subtraction of the two. It's a real clean kind of process. Drop the parentheses. We're changing signs over here, collect like terms, and we get this. So f minus g of x is 3x minus 6. Now, suppose we take the same two functions we had before, and we want to find f minus g of 7 of a particular value. There are actually two ways that we can proceed here. We can say, well, gee, we understand that this notation means the subtraction of functions, but now the x has been replaced with 7. So really, what we're talking about here is f of 7 minus g of 7. And we can follow our nose through that kind of notation. F of 7 means in the f function, replace x with 7 and evaluate. So in that f function, we replace the x with 7. So that's 4 times 7 minus 1. You see, and then minus g of 7 in the g function, replace x with 7 and evaluate. So this x would be replaced with 7, so we would have 7 plus 5. And now, let's see, we did 4 times 7, 28, minus 1, 27, and then here we have 12, 27 minus 12, 15. Another way to deal with it, though, is like this, that using this notation, we can think, well, we've already figured out f minus g of x. We know that f minus g of x is 3x minus 6. We just figured it out in the previous problem. You see, you find the f minus g of the variable first, and then f minus g of 7 means in this f minus g function, replace x with 7. So here's the f minus g function, and we replace x with 7, and we get 15 as expected. So really, when we are adding and subtracting functions, and then in a moment multiplying and dividing, we're really defining a new function. We have a new function, and we could say that its name is whatever operation we're performing here. Multiplication, same idea. F times g of x means f of x times g of x. And for the functions we've been talking about, it would be 4x minus 1 times x plus 5, performing the indicated operation. Here we go. F over g of x means the division of the function, so it's just f of x over g of x. And the f function was this, the g function was this. Now do notice here that because we have the introduction of a variable into a denominator, we have a limitation on the domain. And the original functions didn't contain that kind of limitation, that the domain here for this expression, the acceptable replacements for x, would be all real numbers. And for this one, separately, would be all real numbers. But when we make a quotient out of them, we have a situation where we can't let x take on the value negative 5, and so we have a limitation on the domain. So it's kind of a nuance in this situation of fundamental operations on functions, where we have to kind of look at the situation involving domain as we get to an answer. Here we have f of x and g of x, different functions now for a change. F over g of x would be this quotient then. And now think about the domain. Well, we have a limitation on the domain in the numerator because we're talking about the square root of a radicand that must be positive or 0. And the values of x that will cause the radicand to be positive or 0 are values that are x that are 3 or greater than 3. So x is greater than or equal to 3 for the domain of that numerator. And the denominator has a limitation as well. The limitation is that x can't take on the value 5. So the domain then of this quotient function, this quotient idea, would be this. Now, if we swap it around, if we just flip this over, it's a little bit different. We have to consider it somewhat differently although it's very similar, but we just have to consider all the parts here sort of separately. G over f of x, the g function over the f function. You see, and now think about the limitations. Well, we can't have the value of the denominator becoming 0, and we can't have the radicand becoming negative. So let's see. For the radicand not to be negative, x would have to be greater than or equal to 3. But x can't be equal to 3 because it would cause the denominator to be 0. So we have a strict inequality then for the domain x is greater than 3. Suppose f of x is 4x minus 1, g of x is x plus 5. Now, it turns out that we can actually perform an operation, a new operation, where we put one function into another. Now, this is called the composition of functions. And it works like this. The notation is f of g of x. If we're putting the g function into the f function, this is the notation. Now, let's just kind of go through with the bracket notation here. Working inside the bracket, we would replace g of x with the expression for g of x. So this would be f of x plus 5. Now, this says in the f function, replace the x with x plus 5. So we're replacing x with x plus 5 in the f function. So instead of 4x minus 1, it's 4 times binomial minus 1. So 4 times x plus 5 minus 1. And then we would clean this up a little bit. 4x plus 20 minus 1, 4x plus 19. All right, so that's the idea. Now let's go the other way. Let's compose the two functions in the other direction. That is, let's put the f function into the g function. So it's g of f of x. And following the notation, it's g of, well, what is f of x? F of x is the 4x minus 1. And then g of that means in the g function, replace x with that binomial. Here's the g function, replace that x with this binomial, and we would have 4x minus 1 binomial plus 5. So 4x plus 4. We can even put a function sort of into itself. That is, f of x means we're going to put the f function into itself. So it is f of, now f of x is 4x minus 1. F of that binomial means in the f function, replace x with binomial. So the f function is 4x minus 1, so it's 4 times 4x minus 1 minus 1. We clean it up, we get 16x minus 5. Now, there is another notation for the composition of functions, and I'd like to show that notation to you. This is the easiest one to follow, but another notation for this is this. And I'll use it in all three places. This would be f of g of x would be f of g of x, like this. Now, this is not a 0, and it's not an O, a letter O. It's just a little bitty circle kind of thing. And students read this as fog x, but f of g of x is what this says. That's the notation for it, and this is the equivalent notation. And I suggest that if you see this, you write that, because it's easier to progress through this than it is that, because we're unfamiliar with this somewhat. Now, this one would be gof x, or g of f of x. And when we're putting f into itself, it is f of x, like this. But we would write this and proceed from there.